Hello everybody, and welcome back. Michael Wayne here. As you can probably notice, today we're going to learn about projectile motion. Okay, so we have to have prior knowledge about two specific topics before we can do this. First one is we must know about vectors. And second one is we must know about uniform acceleration. Once we acquire knowledge of these two topics, we can learn how to do projectile motion equations. But first, let's start off with an example. A boy kicks a rock off a 300-meter high cliff. At an angle of 10 degrees with, let's say, 5 meters per second. How far away does the rock land from the base of the cliff? Okay, so there are three things we need to absorb in the information they give us. 300-meter high cliff, 10 degrees and 5 meters per second, and the question, how far away from the base of the cliff? Okay, so our first step is to draw a picture. Here's our cliff, there's the base, 300-meter cliff, the little boy kicking the ball, my bad, the rock. So 5 meters per second at an angle of 10 degrees. And x, which we don't know. So our second step is listing what we have. For our x components, we have velocity initial x, velocity final x, acceleration x, and distance x. And then we'll put time in the middle since the x and y components share time. We'll do the same for y. Velocity initial y, velocity final y, acceleration y, and distance y. So we know the cliff is 300 meters. So actually, wait. Put all equal signs here. Okay, so we know the cliff is 300 meters. And we count that as down, so it's negative 300 meters. Acceleration is gravity, so negative 9.8 meters per second squared. For acceleration x, it's 0 meters per second squared. Not accelerating at all. And dx is what we're looking for. So now we have to move on to what to do next. We have to find the velocity initial of x and the velocity initial of y. So we're going to use trigonometry. Here's our 5 meters per second at an angle of 10 degrees. Okay, so next we have y. And we have the x. We're going to use our good friend SOHCAHTOA to find out what to do. So ka is going to equal to x. So is going to equal to y. And we don't really need TOA right now. So get rid of that. Okay, let's start off with the x. So we have cosine 10 is equal to x over 5. Multiply both sides by 5. We get 5 cosine 10 is equal to x. Rearrange that so it's better to see. X is equal to 5 cosine 10. And if we multiply them, we get x is about 4.92 meters per second. So now let's do the y. We have sine 10 is equal to y over 5. Do the same thing, multiply both sides by 5. We get 5 sine 10 is equal to y. Rearrange, y is equal to 5 sine 10. And if we multiply them, we get y is about 0.87 meters per second. Okay, the reason we know it's meters per second is because velocity initial was 5 meters per second. So we put that into, or we divided it into the x and y components. And so x initial, or x velocity initial is 4.92 meters per second. And initial velocity for y is 0.87 meters per second. Okay, so now we have our velocities. We're going to plug in this changes actually, make them about, we can change it to 4.92 meters per second and about 0.87 meters per second. So we're done with the vectors. So here comes the uniform acceleration part. We need to know about the 4 uniform acceleration equations. The first one is Vf is equal to Vi plus At. The second one is d is equal to 1/2 Vi plus Vf t. Third one is d is equal to Vit plus 1/2 At squared. The last one, number 4, is Vf squared is equal to Vi squared plus 2Ad. You might have noticed something here though. Each equation is missing one variable. The first one is missing d, the second one is missing a, the third one is missing velocity final, and the last one is missing t. To use uniform acceleration equations, we must know 3 variables, and y knows 3, x has 2. So we're going to have to use y to find out t. So we take these 3 and try to solve for t. Since the third equation doesn't have Vf, you would think that we would use Vf. However, that's not the case. If we did use it though, we'd have to put it into quadratic formula and solve that way, as you can see here. So, an easier way to do it is use equation 4 to solve for V final. There we go. Once we've solved for V final, we can plug that into the first equation to get time. Okay, so write out our y variables. Velocity initial of y is about 0.87. Velocity final of y, we don't know. Acceleration of y, negative 9.8 meters per second. dy, negative 300. And t, we don't know. First, we'll solve for velocity final, and then time. Okay, so we're going to use the fourth equation. Vf squared is equal to Vi squared plus 2AD. So we're just going to plug in the variables already. Vf squared is equal to 0.87 squared plus 2 times negative 9.8 times negative 300. Multiply those numbers, we get Vf squared is equal to 0.7569 plus 5880. Add those up, and we get 5,880.7569. Square root that, and then we get Vf is equal to, or about rather, 76.69 meters per second. So now that we got velocity final, we'll plug that into the first equation. Oh yeah, velocity final has to be negative since it's going down. So Vf is equal to Vi plus 8t, Vf minus Vi, divided by A is equal to t. Just a little algebra we did there. Substitute the variables. T is equal to negative 76.69 minus 0.87 divided by negative 9.8. So when we do all that, time is about 7.91 seconds. Okay, so we're going to take this second, or these seconds, and put them into the list that we have. So now it has 3 variables. So luckily we can use the third equation because the acceleration is 0, so it'll cross that one out. So we're going to use it. So same thing we did with y, list out our x variables. V initial of x, which is about 4.92. V final of x, we don't know. Acceleration of x, 0. D of x, that's what we're trying to find. And t, 7.91. So we write down the third equation. D is equal to VIT plus 1/2 AT squared. Okay, that's 0, so cross that out, 0. So now we're just left with D is equal to VIT. Plug in the variables and we get D is equal to 4.92 times 7.91. Multiply that, D is about 38.9172 meters. So it lands that far away from the base of the cliff.